So at some point in, I believe, chapter 7 of your text, if you're in my class, you were introduced to the spring force minus kx, where k is the spring constant, the measure of the spring stiffness, and x is the position, but this is the position measured from a really specific point, which is the equilibrium position of the spring. All right, so if I'm going to determine the work done by a spring while moving, either the work done by a spring or the work done against the spring, moving an object from point to point, I can determine that with just my formula of work. And let's just worry about the magnitude of this so I can get rid of the negative sign. We're going to talk about the negative signs and what that means at the end of this video. But for now, let's get rid of the negative sign and just deal with the magnitude. So I'm going to get the magnitude of the work here from point A to B of F dot dr. Well, if I'm just looking in the x direction, then this force is all in the x direction and my displacement is all in the x direction. I'm going to insist that this is a one-dimensional system, that everything is in the x direction. If that's the case, I just get the magnitude of the force times the magnitude of the generalized displacement. The angle between them is going to be 0 or 180 degrees. I'm going to get a magnitude of 1 out of that. So this simplifies to just integral kx dx, where I've replaced my generalized dr with my dx. I've replaced my force with the kx, and I've thrown away the negative signs because I'm looking at the magnitudes. All right, k is the spring constant. It's going to come outside the integral. K times the integral from a to b of x dx. I'm going to get from that k times 1/2 x evaluated from a to b. All right, so I'm going to get 1/2 k x sub b squared minus x sub a squared. And I've done this before. If I realize that a is my initial position and b is my final position, let me change these subscripts to something that's a little bit more general. 1/2 k x final squared minus x initial squared. If I just assume that the initial position is x, now here's the general equation, right? This is where we should stop and say, okay, this is the work, at least the magnitude of the work done by a spring on an object if it moves it from this position to this position. Now, how we normally write this is this. We assume that our initial position is 0. This, if we're trying to develop the idea of potential energy, we talked before how you can always set your 0 point at any place. You can move your origin. Let's move our origin to where I was initially. And so I usually see this written like this, 1/2 k x squared, where the implication is that x is the final position. Sometimes you'll see it written as 1/2 k delta x squared, which is a little bit more, no. 1/2 k delta x squared, sorry, not delta x squared, delta of x squared. I don't normally write it like this, but occasionally you will see this written. I usually stick with this, and if we need it, I'll go back here. But this is the work done by a spring. Now, here's the punchline. Spring forces, or elastic forces as they're sometimes called, are conservative. So what can we say about that? Well, we can now say that the work done by the spring is equal to the, remember from last video, negative change in potential energy. And again, I'm really playing fast and loose with my negative signs here. We're going to talk about this negative sign and what it means at the end of this video, so just hang on to that. But for now, what we are normally going to do is say that the potential energy stored in a spring, U spring, or sometimes subscripted with an E for elastic, but I don't like that. U spring usually is written like this, 1/2 k x squared. We saw in the last video, U gravity we can calculate as mgh, as long as we make the stipulation that we're at or near the surface of the Earth. Here is mgh. So these are two types of potential energy with which we are going to deal. We're going to investigate problems in which energy is stored in a spring, and energy stored, we'd say it's stored in the gravitational field. Now, of course, if it's stored, we allow it to move into kinetic energy. So in a lot of situations we're going to find the kinetic energy of an object by looking at something having to do with the potential energy. To get that, we're going to need to explicitly evaluate or explicitly investigate the conservation of energy, which we're going to do in the next video. But for now, let me talk about this delta U and the negative sign. So what I've said so far, and I realize that I'm summing up a lot, but that's okay. The work energy theorem tells me that the net work done on an object is equal to the change in kinetic energy. And then I said, if the force is conservative, I can say it's this negative of the change in potential. This is for conservative forces only. So if I'm dealing with a conservative force, which I am currently, if this is true, what I can say that delta K is equal to negative delta U. And so we don't hardly ever, at least I don't usually ever write it in this particular form, but we are going to use something that looks similar to this in the future. But let's talk about what this means. What this is saying is that if an object has kinetic energy, and it has been under the impetus of a conservative force to get that kinetic energy, that we can consider that energy to have come from a potential energy associated with that force. Here's what the negative sign means. It means that whatever used to be potential has now become kinetic, right? If I have lost some potential, that means I have gained some kinetic. I could go the other way. I could lose some kinetic and gain some potential energy. Think about if you're looking for the first one, lose some potential energy and gain some kinetic. Think about dropping the pin, right? It has potential. As I drop it, it loses potential energy, but that potential energy is coming over into kinetic energy. So the negative sign tells you that however it changed here, that change appears here in the kinetic energy. Going the other way, you can think of an object moving with kinetic energy and crashing into a spring and compressing that spring until it stops, right? I'm putting potential energy into that spring. Where's the potential energy coming from? From the kinetic energy of the object. So in that case, my delta K would be negative. My delta U would be would then become positive, right? Because I'm putting energy in. So this negative sign, like I said, even though we don't normally write it like this, this is really, really important to understand, because this tells you kind of have a weird bank account going on here. You have a bank account with two separate accounts attached to it. And for now, we're not letting anybody put any money into either account or take any money out of either account, but we can move money from one account to the other. So as my potential account gets low, my kinetic account gets big. As my kinetic account gets low, my potential account gets big, right? As this thing falls down, the kinetic energy increases, but the potential energy decreases. Same thing would happen with a spring. So that's the idea. And very soon we're going to start letting people make deposits and withdrawals. We're going to have work done, which crosses the boundary of my system. It opens up my bank account to outside influence. But this is a good way to look at it and a good way to think about it. The idea that if you're dealing with conservative forces, any kinetic energy that comes from one of those forces can be considered to have come from some sort of reservoir of potential energy.